In this question, our task is to find the value of this resistor. And it's always a good idea to start off with any circuits question and just writing on what you know about it. So the question tells us that the voltage drop across the diode there is 1.8 volts and that the current through the circuit is 20 milliamps. And a general tip for circuit questions is if you're sitting there thinking, oh, I don't know where to start, pull out V equals IR and just work around the components, writing down what you know and what you can work out. So, looking at the value of R, which is what we want, we can't find that. We do know the current through R, it's 20 milliamps because it's connected in series, but we don't know the voltage across it, and that obviously is going to be our task. However, looking at the internal resistance, the 10 ohm resistor, we obviously know its value and the current through it. So it's really just a question of V equals IR, bunging in the values, 20 milliamps times 10 ohms, and that gives us a value of 0.2 volts. So we've just worked out that 0.2 volts is dropped across the internal resistor. This means that we can now say that the voltage across the big resistor outside the load resistor is going to be 5 volts, the EMF, take away 0.2 volts, take away 1.8 volt. And if you work all that lot out, you get a voltage of 3 volts. So now we know the value of the voltage, 3, across the resistor and the current through it, 20 milliamps. So once again, it's back to Ohm's law. This time V over I equals R. Substituting in the values, 3 volts divided by 20 milliamps gives us a resistance of 150 ohms. So the answer is C. Here's another question from the AQA multiple choice gallery of wonderful questions. This time again about EMF and internal resistance. And in this circuit we have a voltmeter which is reading V volts, and we're told that things change as we close the switch. And we're asked to calculate, work out the internal resistance. Now, because of the way I was brought up to do physics, the first thing that I'm going to do is draw in an internal resistor there. Now you might think, well, what's the point of that? I know it's there. Well, good for you. I just find it's much easier to write everything down. Now, at the moment, we are told that the voltmeter V is reading V. It's actually measuring the terminal PD, isn't it? So we know the terminal PD, in this case, is going to be the EMF because there's no current flowing. Since there's no current flowing in the circuit, the voltmeter is actually going to be reading the EMF of the cell, which is also V. Things change, however, when we close the switch. So now we've got a closed switch. And immediately you will see that we're going to get some current. And of course, that's going to be quite a big current because 2 ohms is a fairly small resistor. Well, in fact, it's not fairly small, it's a pretty darn small resistor. How's that going to change things? Well, we are told that this reading now goes to V over 3. In other words, with a third of its previous value, which means that somewhere in the circuit, we've lost 2/3 of a volt. Firstly, why is that? Well, as we said, it's because we've got significant current flowing in that circuit, and that is travelling through little r, the internal resistance. And of course, from Ohm's law, V equals IR. If you've got a current, you've got a resistance, there's going to be a voltage change across that component. Secondly, we can see that the voltmeter is actually measuring the voltage across the 2 ohm resistor now. If you follow the wires back, you can see that. It's also the terminal PD, of course, but we're interested to know that it's actually the voltage across that resistor. The only other place where voltage can be lost in the circuit is, of course, across the internal resistor. And we know that is going to be 2 over 3V. Now, of course, you will recall that in series circuits, resistors share out the voltage in proportion to the value of their resistance. But that's what we've got here. We have a series circuit with a little internal resistance connected to a fairly little external resistance like that. In other words, the voltage of the value of the EMF is going to be shared out between those two components. We know this is V over 3. We've worked out that this is 2V over 3. Therefore, if we know that this is 2 ohms, we have twice as much voltage across the internal resistance. It has to have a value twice as much as the external resistance. Therefore, R is going to be equal to 4 ohms. And once again, that means it's C. Another way to think about this sharing out is to consider using the potential divider formula. So V out equals V in multiplied by the resistor you're measuring across plus the total resistance. I'll leave you to work out how to use that. And yet another way is just to realise that because we've got fractions of with a 3 underneath them, in other words we've divided the voltage up to 3 slots, we have to have the same 3 units as it were of resistance. So one is 2 and the second resistance is 4 ohms, i.e. 3 lots of 2.